We're going to look at Riemann sums here, which is a way to standardize area calculations. So if something can't be geometrically calculating the area under the graph, we can do it using this idea here. So the process for a Riemann sum is to first divide the area into rectangles. Next, you're going to calculate the area of each rectangle. And then finally, add the areas together. So when we divide this area into rectangles, basically, I'm just going to draw rectangles that are roughly the right size. I'm going to draw a bunch of these that roughly approximate the area under this curve. And how I'm doing it is I'm just setting the height equal to the function at one of the points. And then I've just split it up into a bunch of rectangles like this. So you can see how the area enclosed by these yellow rectangles is going to be roughly equal to the area of the total curve. And if I make these rectangles even smaller, I'm going to get a more and more accurate estimation of it. So the types of Riemann sums that you have. There's the left-hand sum, the right-hand sum, the midpoint sum, the trapezoidal sum, the lower sum, and the upper sum. Left-hand sum is use the leftmost x value to calculate height. Right-hand sum is use the rightmost value to calculate the height. The midpoint sum is use the middle x value to calculate the height. Trapezoidal sum is to average left and right heights. Lower sum is use the smallest height. And upper sum is to use the largest height. And these are the heights of those rectangles. And so this next illustration I think is going to help clarify everything here. So first, this one we have is a left-hand sum. Sorry, I'm not sure why we're freaking out here. So this is a left-hand sum. This next one is a right-hand sum. This third one is the midpoint. And this one on the right is the trapezoid. And then you can see lower and upper sum on the bottom. So you'll notice the left-hand sum, each of those rectangles, all the way to the x value, that's where we set the height of the rectangle. For the right-hand sum, all the way to the right of the rectangle is where we set the height. For the midpoint, it's in the middle. You can see we take the middle x value to set the height of a rectangle. And then the trapezoid was setting it, the two endpoints, and kind of creating a trapezoid which functionally finds the average height. Then you'll notice with lower and upper sum, they just found the place in the entire range that's either the smallest value or in the upper sum, the biggest value. These last two are kind of weird. We won't ever really calculate anything with them in this class. But they're good to be aware of because there'd be reasons for like computer science or engineering that you would use, for example, lower or upper sums. So now we want to talk about over versus under estimates. So for monotonic functions, monotonic means that it's either always increasing or always decreasing. The left and right-hand sums will either overestimate or underestimate, and those should be kind of easy to reason out once you're familiar with this. So if it's always increasing, you'll notice a left-hand sum will always leave gaps that it doesn't quite cover with my kind of quick sketch here. So there's always going to be gaps left in, so a left-hand sum for a constantly increasing function will underestimate because there's missing bits. Meanwhile, for a decreasing function, a left-hand sum is going to overestimate. And then the reverse is true for right-hand sums. If it's monotonically increasing, the right-hand sum overestimates. And the decreasing function, the right-hand sum, underestimates. So this is just something that as you work, the AP likes to ask this, and so just get used to kind of reasoning and thinking through it.